Okay, that sounds great. Thanks, Julia. Okay, well, welcome everyone. I'm Emily Sherbo. I'm the president of the Mass Rivers Alliance Board of Directors. Welcome to our 2025 annual meeting for our organization. So we're going to go, I think, to the next slide for the agenda, right? There we go. Okay. So here's today's agenda. We will start with our business meeting, briefly review some of the highlights from this year, and then we'll turn it over to our guest presenter. Um, okay. Give everyone a minute to read this. I see people are still entering, so we'll let a few more people in before we do our board election results. All right, I think we can go to the next slide. Okay, so as a reminder, our bylaws at Mass Rivers Alliance stipulate that the organizational members are our voting members and they elect our board members. Over the past several years, we've held the election with proxy ballots, and we need a simple majority of our members to vote in order to elect the board members. So big thank you to everyone that took time to vote. Before I get to the voting results, I just wanted to make sure everyone has seen our three board members that are up for re-election. We have Jackie, Mary, and Deirdre, and they're both wonderful board members. So I will turn it over to Paul Boulier, who is our clerk, to give us the results of the vote.
Thanks, Emily. We had 47 proxy ballots cast in favor of the slate. We have 85 organizational members, so that's more than a quorum. So this slate has received a positive vote for renewal of their terms. Yay.
Yay. All right, thank you, Paul. And congratulations to Jackie, Mary, and Deidre. And thank you so much for your service in the past and for your continued service on the board. It's a pleasure working with you. And with that, that concludes our official business. Pretty straightforward. So I am going to turn it over to Julia Blatt, our executive director, who will introduce the staff and speak for a moment.
Thank you, Emily, and congratulations to the three continuing board members. Thanks to everyone who's joining us right now. I can't see you, but I know you're there, and I'm glad you're there. So first, I thought for those of you who haven't met any of some our staff, here they are. From left to right, that's Anna Renkert, our Development and Engagement Coordinator. That's Heather Klisch next, our Policy Director. Then there's me. Lydia Olson is our Technical Specialist. Monica Driggers is our Deputy Director. And Andrea Eigerman is our Grant Programs Manager. And we have one more team member who's not in the picture, Victoria Keir, who's our bookkeeper and office manager. So if you see us out in the wild, please say hi. It's a wonderful team, and I'm very, very proud of the work we do with not that many people. Okay, next slide. So just really briefly, year in review, some of the highlights. We had on the top left and below, you see Lobby for the Rivers Day. We had about 61 people join us, and we met with 53 legislators, I think, and their aides during a very rainy day recently. And so thanks to those of you who are able to join us. We have our top three priorities that we talked about for that were the drought bill, the Nature for Mass bill, and a bill that would create statutory authority for the Division of Ecological Restoration. So thanks to everyone who came out for those three priorities. We also had a series of, we call them rainwater readiness workshops to help people with stormwater management and funding. And you can see that in the middle. That's a rainwater readiness workshop. We, as most of you know, Dam Busters is has become a real signature program for us. And this year we had 10 webinars and 2 in-person site visits, and then 1 workshop in person. And that is a picture on the bottom of a site visit to a dam removal site in Pittsfield. Um, keep going. And speaking of Pittsfield, we also just made a visit out there to meet with some of our Western member organizations. And you can see, and special shout out to BEAT, the Berkshire Environmental Action Team, who hosted us and helped set that up for us. That was a wonderful experience for us. We don't get out west as much as we'd like to, and we were really excited to do that. Our entire staff went, as well as several of our board members. Let's keep going. Um, and then, oh, last but not least, we had a wonderful party last month, or it was last month, I guess. And we had about 200 people come out to celebrate as a community. So thank you all for coming. And if you missed it this year, we'll do another one next year. And we hope that we see you there. I think let me make sure I didn't miss anything important. Oh, I just did want to point out that of our team that you saw, two of the team members just joined us this year. So special note, Heather Klush as policy director is new, as is Andrea Eigerman, our grant programs manager. So, I hope when you see them, just make sure you welcome them. And that's it. So I thank you for supporting all the work and for being part of it. And we're just grateful to have this community. I think with that, I'm going to now turn it over to Monica to introduce our speaker.
Hi, everyone. I'm Monica Driggers. I'm the Deputy Director of Mass Rivers. I'm really pleased today to introduce Dr. Rebecca Hale. She's an ecosystem ecologist who works at the interface of biogeochemistry, hydrology, and society. In addition to traditional ecological methods, she adapts concepts and tools from geography, sociology, and history to ask fundamental ecosystem ecology questions in non-traditional settings. Dr. Hale works within and across cities and rural areas at local to regional scales, and she has done a lot of work in Massachusetts, so we're very excited to hear about her work. Welcome, Dr. Hale.
Hi, thank you so much. I'm so excited to be here. I grew up in Massachusetts, and so I have a deep love for the state. I actually did look on a map while we were talking about what watershed I grew up in. It was Island Creek watershed, so tiny, tiny little watershed, right next to the coast. And then I went to school out in Western Mass for my undergraduate, before leaving out west for a long time. So today I'm going to talk about urban streams and some of the work that I've been doing in urban streams, and really thinking about kind of how our relationships have changed with streams through time, and some of the efforts that are happening now to reconnect us with those streams. Make sure there we go. So urban streams are really important opportunities within cities for humans to connect with nature. We often think of cities as being kind of the opposite of nature, but they really are not. We are part of nature. Cities have lots of nature within them, and streams provide a really important opportunity for us to recreate, to see water, to see life, and really connect with our surroundings. But that can be really hard because urban streams are often buried underground. A lot of streams were buried when we first urbanized, a lot of times for good reason, because they were full of lots of waste, and were dangerous. Or they're inaccessible, so lots of fencing. These are pictures from Baltimore, which has a lot of inaccessible urban streams in it. Or you can get to them, but you don't necessarily want to, because they have really poor water quality. And so I'm just going to give kind of an overview of some of the changes that happen to streams from urbanization before digging in more. Sorry, I'm going to try to move this Zoom thingy. All right. So urbanization really dramatically changes watershed hydrology. So if we think about, a natural, quote unquote, environment that is trees and grass and no impervious surfaces, then when rain is falling from the sky, a lot of that's going into the ground and a lot of that's evaporating, and very little of it is going to streams as surface runoff. Most of that's coming more slowly through the groundwater. And when we urbanize, we put down a lot of buildings, we put down a lot of impervious surfaces, and that means that there's much less of that infiltration into the ground. Much more of that water is leaving as runoff, and then because we have less vegetation, there's less of that evapotranspiration back up. And so that has really big implications for our streams. They are kind of subjected to this very flashy hydrology, where when it rains, that rain moves very quickly to the storm. That water is moving very fast. It has a lot of power, and so it's eroding stream banks and moving a lot of sediment through the stream. And then you also have, because you don't have that infiltration, a lot of urban streams also have lower water tables. And so base flow is actually getting lower through time. So you see these really dramatic changes in the hydrology and the geomorphology of urban streams. Urban streams can also be really hot, and they can have really low dissolved oxygen. So these are data from some streams in the Boston area, Alewife, Beaver Brook, and Stony Brook. And I did not collect these data. This was part of a large collaborative project that I did lead, but Allison Roy at USGS and UMass was the lead PI on the Boston work, and Annika Quick, who's now at Virginia Wesleyan University, did all the actual work here. So these are 3 streams that we monitored for a year. So Alewife Brook is the most urban one, and then Beaver Brook is more suburban, and Stony Brook is more rural. And so we can see, looking at the water temperature, that as you urbanize, you have hotter streams. And that happens for lots of reasons. One, you have those highly connected impervious surfaces, and so when rain falls, then it's interacting with these hotter surfaces and moving to the stream. And then also you have that loss of vegetation, that cooling. And then partially because of that temperature, but also because of some other things, you have really big changes in dissolved oxygen concentration. So again, here's Alewife Brook, this red one. And this line here is the hypoxia threshold. So it's not so great for most aquatic life. Below this threshold, and you can see that during the summer, when the stream is really hot, the oxygen is really, really low in these urban streams, and we don't see that same kind of pattern in the less urban streams. And then overall, urban water quality is often quite degraded. So this is, again, these 3 streams from Boston showing conductivity through that year. And again, here's Stony Brook is this blue one at the bottom. And this black line here is the threshold for acute toxicity for aquatic life. And you can see that for the more suburban and urban streams, much of the winter, they're above that threshold for acute toxicity. It counts as acute toxicity if it's over this threshold for more than an hour. And you can see it's often for much longer than that it's above that. And this is because of road salts that are being added to the streams, but there's lots of other things that we do. There's the salts, nutrients, pesticides and herbicides, pharmaceuticals, oil and grease, heavy metals, tire chemicals, all sorts of things that are impairing the water quality of urban streams. But not all urban streams are the same. Cities are really heterogeneous. They're really variable ecosystems. And this is what gives me a lot of hope and also fascinates me about these ecosystems. So, for example, in Miami, this map is showing variation in septic density across the city. So you have areas that have really high septic density and areas that don't. In Baltimore, for example, lots of variation in canopy cover across the city. In Arizona, a place where I did my dissertation work, lots of variation in the types of stormwater infrastructure that are used across these cities. So this is really exciting because not all urban streams are the same. They're all kind of doing their different things. They're reflecting those watersheds. And so a lot of my research is trying to understand, how do urban watersheds shape urban streams? And then can we use this to understand how to make our urban streams better? How do we use this to improve the conditions in our streams? So I'm going to talk a little bit, I'm going to continue with some Boston data and kind of talk about this larger project that we've been doing, trying to understand kind of how urbanization shapes water quality in different cities. And urbanization really shapes lots of different aspects of urban watersheds. So we have, additions of different types of pollution sources. We're changing land cover, we're changing vegetation, we're changing the hydrology. And a lot of this project is trying to understand, well, and so I'm getting ahead of myself. I changed my slides for this talk. So one of the tools that we're using is dissolved organic matter. We can think about dissolved organic matter as kind of the tea of the watershed. So it's all of the materials that are leaching into the water. So the leaves and the soil and whatever kind of microbes are hanging out in the water and the soils. And that can tell us a lot about watershed function. And I'm going to kind of walk through how we use this within an urban context. So as we urbanize, we end up, so here I'm going to show a few graphs with impervious cover, so parking lots, streets, buildings, etc. As we urbanize, as we cover up those soil sources, good Lord, soil sources of dissolved organic matter. So when it's raining, it's going to come through. That water is going to pull organic matter from the soils and bring that to streams. As we urbanize, we lose that organic matter that's coming from soils that we describe as humic organic matter. And we also see increases in organic matter that's coming from the stream itself. So when we urbanize, we often have increased light availability because we've cut down a lot of the trees along the riparian canopy. We have those warmer streams, there's more nutrients, and so basically great conditions to feed algae, which are then that organic matter is going to kind of leach out of them as well. And so we see increases in what we call autochthonous, so stuff that's produced within the stream, DOM that's coming from within the stream. And then we also see increases in microbial organic matter. So organic matter that's coming from pet waste, from human waste. Any kind of, and those warmer conditions are also kind of stimulating more of this microbial organic matter. And these data themselves are from the Boston area and published in this paper that Annika published earlier this year. But we were really interested in understanding, okay, so it's not just impervious cover. I just talked about all the different things that are going on. So what is it about urban watersheds that shapes dissolved organic matter and what that looks like? And what we found in the Boston area is that it wasn't necessarily development per se, but it was actually the loss of wetlands that really shaped the quantity and the quality of organic matter across the landscape. So here on this plot, we're showing that humics are more soil derived to autochthonous, so algae in the stream. And as you lose wetland cover, you start going from more soil derived in these higher wetland watersheds to more of the in-stream production in the watersheds that have less wetland cover. And this was a really striking gradient that is pretty specific to the Boston area. So our other cities don't have that because they don't have that same kind of range of wetland cover. So in Boston, it's really wetland loss, less so than development itself. But then we also found that combined sewer overflows have a unique dissolved organic matter signature. So this measure here is what we call tryptophan-like dissolved organic matter. It's basically an amino acid, a protein-like organic matter that is produced by bacteria, including E. coli. So it's going to be associated with wastewater. And lots of studies have found that this is strongly associated with wastewater. What was really interesting is these different colors are the 4 seasons that we went out and sampled. And by we, I mean Annika. And this one was really dry. The purple season, that was during the summer. There hadn't been any rain in a long time. And so we didn't see this x-axis here is combined sewer outfall density. And so we didn't see that affected anything during the dry period, but as soon as it was wet, we saw huge increases in this tryptophan-like dissolved organic matter, suggesting that these CSOs are kind of a unique contributor to the organic matter pool. So in some of the other cities, we've also found that household income can be a key driver of organic matter, which is a really interesting finding because there's money is not causing organic matter to do anything, right? So in Baltimore, Maryland, for example, we've done similar sampling and found this is a measure of how microbial or how terrestrial the organic matter is. And we find that there's more microbial dissolved organic matter in watersheds that have lower median household income. And we also see the same kind of pattern in Salt Lake City. Here we're using a different metric called peak T, which is basically the same tryptophan-like dissolved organic matter. So we see that lower income areas have more microbial, more wastewater influence dissolved organic matter. And this is really interesting. It makes a lot of sense in a lot of ways because often provision of government services, the kind of when you look at like where restoration happens, where best management practices happen, those usually tend to happen in wealthier areas. And so in this sense, the income, what we're starting to see here is that income seems to be this integrator of kind of where preferable housing is, where services are being provided across the landscape. So for example, in Salt Lake City, it's not elevation, it's not tree cover, it's not necessarily like how many treatment plants are upstream of the site. It's income like integrates all of those different patterns across the landscape. And yeah, so overall, we're seeing more microbial organic matter in lower income watersheds. Okay, so we can learn a lot about urban watersheds from dissolved organic matter, and it's especially potentially powerful to understand wastewater inputs. So the next kind of story I'm going to pivot to here is thinking about whether we can use dissolved organic matter to better understand recreational water safety. And this is some work that we've been doing in the Anacostia watershed, primarily in the Maryland suburbs of DC, but a little bit in DC as well. So across the Anacostia, so here DC is here, and then these are all tributaries going into the Anacostia River. This is data from the Anacostia Riverkeeper report from last year, showing the percent of observations. They go and do biweekly sampling from May through September. And if it's red, it means it failed. If it's green, it means it passed for a threshold of 410 most probable numbers per 100 milliliters of E. coli. So you can see that a lot of these streams are in really poor condition. This is a picture of my children a bunch of years ago playing right here before I knew how bad the water quality was. Right there, but a lot of these streams are not safe for recreation across this area, and they're designed in this way that's very inviting, and little kids play in them all the time. But the challenge here is that the water isn't always gross, and so when do people know that it's safe, that it would be okay for them to go and play in it, and enjoy these really beautiful resources? So one of the things that the Riverkeeper tells people is that if it's rained more than half an inch in the last 3 days, just don't go in the water. So here we have, here's your half-inch kind of threshold, and then I have E. coli on the y-axis here, and they basically say this is the actual threshold for definitely don't get in the water. So this is great if it's E. coli is generally high after it's rained half an inch in the past 3 days, and generally low when it hasn't. Then that's a really nice kind of rule of thumb to tell people that if it's rained, just don't get in. But the problem, these are some of the sites that they've been sampling over the past few years. That rule fails for 70% of these sites where we have, and these are huge numbers here. This is on a log scale. So this is, over 1,000 MPN per 100 milliliters. So for lots of these sites, we have really high E. coli, even if it hasn't rained at all. And so then the question really becomes, how can we predict what's going on in these sites? So this is a project that's been funded by the Chesapeake Bay Trust. We started last February. And it's in partnership with, it's my lab, the Watershed Science Lab, as well as the Coastal Disease Ecology Lab at CERC, and then the Anacostia River Keeper. And we're trying to understand a couple of questions. One, just why are bacteria levels so high? Where are those coming from? And how do the sources vary across the watershed? So my colleague Katrina Lohan, and Megan Stollard here, she's a postdoc working on this project, and she's our she's become just like she's running the whole show. So they're working on doing some molecular source tracking to understand where E. coli is coming from. So is it predominantly human? Is it canine? Is it from birds? And how does that vary depending on flow conditions? How does that vary depending on which watershed we're in? And then the other part of this project is trying to understand whether we can provide kind of real-time information to the public about current water safety. Because right now, what the Riverkeeper is doing is they're collecting this data. It's every 2 weeks, and it's 24 hours later, right? Because they're E. coli measurements, and it takes 24 hours to do the incubation, get the number before you can report that to the public. So lots of times, they go out on Wednesday morning, and then it rains, and Thursday, that data is not good anymore, right? So trying to figure out whether we can provide information, what the possibility of doing real-time data. And we're testing some hypotheses here. So if this is our little stream and we're interested in understanding E. coli concentrations in that stream, there's different sources, right? It could be coming in stormwater runoff from wild or domestic animal, fecal material. It could be naturalized E. coli in the stream sediments that are getting resuspended during those high flows. Or it could be human fecal material that's coming in through sanitary sewage flows, either illicit discharges or overflows or leaks. We don't have combined sewers in this watershed, or at least not in any of the streams that we're measuring. And then what we're doing is kind of linking these to potential proxies that we can measure with a sensor. So that we can have a sensor out there real time collecting data. Can we use that to make a prediction about the risk? So if we're looking at stormwater runoff, can we use turbidity or conductivity or discharge to predict that? If it's naturalized E. coli, are there correlations with water temperature, dissolved oxygen, or turbidity? And then for the human fecal material, potential proxies would be that tryptophan-like fluorescence, so that good wastewater indicator. And then we also have sensors that we're testing for optical brighteners. So these are dyes that are added to detergents, paper, toilet paper, all sorts of things to brighten clothing or paper. And so they can be also high in untreated wastewater. They're usually removed by treatment because they're very photosensitive. So they break down in UV light really quickly. And our goal here is to be able to have sensor estimates of real-time E. coli risk so that we can have this kind of predicted E. coli based on some kind of sensor measurement that then we can communicate to the public. And there's some precedent of doing this, like the USGS has a system in the Chattahoochee where they've developed a real-time monitoring program based on discharge and turbidity. So we're trying to see whether some of these DOM measures can be helpful in understanding what's going on. So here's a map of the Anacostia watershed. The green sites are all the sites that we're getting kind of snapshot samples from throughout the summer. And then these orange sites are where we have sensors. So there's 3 sites that we're monitoring intensively. So we have these multi-parameter sondes. We're measuring all those different parameters I just talked about in the last slide, and then, or 2 slides ago. And then we're going out and collecting samples weekly to look at lab measurements of dissolved organic matter fluorescence. And then we're doing weekly to biweekly E. coli and molecular source tracking sampling. So I'll just tell you a little bit about these 3 sites, and then I'll show you some data. We set these up in last February, started getting data around March. So Watts Branch is this, it's the smallest watershed that we have. It's this one down here. It's in a very disinvested area of the city. And so there's a lot of illicit sanitary hookups to the stream. And so when it rains, you get a lot of raw sewage in there, even though there's no CSOs. there's a lot of wastewater coming directly into that stream. Sligo Creek is up here. If you recall a few slides ago, this one also has really high E. coli concentrations even during base flow. So these are some of the sites that failed repeatedly throughout a whole season. It's slightly more suburban, but also has really high E. coli year round. And then northeast branch of the Anacostia is this really big watershed, so it's integrating just lots of different land cover, and it's much bigger and it has much higher flow. And typically in the past has, behaved well in terms of, E. coli concentrations are low until it rains and then they're high, where we don't see that at Sligo Creek and Watts Branch. So I'm going to jump right into some data. So we're finding, and I will say this is super hot off the press. I was like, I'll just give like the same talk I gave last summer. And then I got really excited about showing you guys some fresh data. And so, yeah, all of this is super hot off the press as of yesterday. But this is Northeast Branch. That's that kind of well-behaved site. And what we find is here, it's actually dissolved organic matter is the best predictor of E. coli concentrations, which I did not expect. I thought that discharge would be a good predictor here. But here, this is looking at the ratio of that tryptophan-like to a more humic-like organic matter. So basically, if there's relatively more stuff that looks like wastewater compared to soil-derived organic matter, then your E. coli concentrations are higher. So this is really cool because it's suggesting that this kind of relative contribution is predictive of kind of how much wastewater is coming into the system. And it also suggests that these really high concentrations are coming from wastewater in this stream. But that doesn't work at all in the other streams, which is interesting and kind of frustrating. So here's Watts Branch. This is the one that we know has wastewater inputs into it. And we can see that that ratio of the more protein, like the more wastewater to soil like is higher in general. There just is more kind of wastewater coming into that system, but I don't know if it's because it's just higher overall or what, but that's not predictive because it's just always higher. And then Sligo, it's not a significant relationship, but it's better than this flat line over here. In Sligo, we actually can explain a lot of the variation in E. coli with the combination of stream flow and this tryptophan-like fluorescence. So we do see an increase in E. coli concentrations with stream flow. So higher stream flows definitely are mobilizing more E. coli, and our highest concentrations are definitely during storms. But we also see the bubble size here is the concentration of that tryptophan-like dissolved organic matter. And so we see even at low flows, if that tryptophan-like organic matter is high, then you're going to have high E. coli. So I'm not sure what's going on here. It definitely seems like there's some possibility that sewers are leaking at low flows. It smells like sewage effluent all the time in this stream. Even though in theory there's not anything coming in, but I think that this is kind of pointing to having a sewage input here. And then at Watts Branch, this most wastewater impacted site, we really have very little predictive power. So we do see kind of a relationship with the amount of that wastewater indicator, but it doesn't explain much of the variability. And sometimes we have really high concentrations that are not, even at really low concentrations of that tryptophan-like fluorescence. And so the jury is kind of still out on what's going on there. Okay, so interactions between the flow and dissolved organic matter here are suggesting that the E. coli sources are really varying with flow conditions and also among sites. And so our next tip here is we're doing this molecular source tracking. Megan is extracting DNA, probably literally as we speak, to be able to do that analysis. And then we'll be able to have a better sense of how some of those sources are varying among sites and also during base flow versus storm flow. And then all the data that I showed you in terms of the dissolved organic matter data is coming from grab samples. The sensor data, we can have like a whole talk about this, um, is much more complicated because they're fluorometric sensors, and so they're measuring light, and so they're very sensitive to turbidity, and then because it's measuring the light that's being re-emitted by organic matter, they're actually sensitive to temperature as well, and it turns out that tryptophan it's really complicated, and so we're doing a lot of work to figure out how we can correct that data, which I think has been a really important lesson for me in terms of how kind of off the shelf ready some of these potential approaches may or may not be. I think it's very exciting that we're seeing these relationships with tryptophan-like fluorescence and the E. coli, but turning that into a real-time product is going to take a lot of legwork to get some data that's really good. And I think there's a lot of implications for setting up like new sites. You have to develop a lot of the relationships within that site. We're continuing data collection through next year, so we'll have a lot more data to be able to develop these models, and then we'll do some more sophisticated models than me just kind of quickly plotting a bunch of stuff right before giving a talk because I'm just really excited about it. And then the other thing is that we have these synaptic sites. So there's these 3 sensor sites, but we have 17 more sites where we have E. coli data going back several years that the Riverkeeper has been collecting. We've been collecting dissolved organic matter data at those sites and nutrient data for the past 3 years. And then we'll have the MST data from this past summer. So we'll get a better sense of how those E. coli sources are varying among these different watersheds, which will allow us to have a better sense of, can we translate like the data that we're getting at Sligo to other sites that have similar E. coli sources. Cool. So this is the end. I'm going to wrap up now. Urbanization reshapes many aspects of urban watershed function. And I think dissolved organic matter is a really powerful lens for understanding urban watersheds, where water is coming from, where it's going, what's happening to it in streams. The water quality impacts of urbanization are not evenly distributed on the landscape, and they're shaped by a whole number of things, but there are definitely inequitable distributions as well in a lot of our cities. And there are a lot of tools on the horizon for improving urban water quality, providing information to the public. And there's a lot of work to be done, I think, to make those really meet their full potential. And I really want to do that so we can hang out in our urban streams. I want to thank you all for your attention and for inviting me. Funding for this work was provided by National Science Foundation, also Chesapeake Bay Trust. And then key collaborators here for the Boston data, Allison Roy and Annika Quick, and in the Anacostia. A whole lot of people at CERC who helped collect all this data, and a bunch of folks at the Anacostia Riverkeeper who've also done so much work. And I'm super excited to take your questions.
Monica, you're muted.
Sorry about that. I want to thank Dr. Hale for a really great revelatory talk. And I think many of us in the audience have suspicions about what's going on in urban streams. What your research is really has a lot of implications for our work on everything from combined sewage overflow to environmental justice to habitat, even urban habitat. And we loved hearing the breaking news in this presentation. There are a few questions already in the chat that I will read. And if anyone else has questions, please put them in the chat. The first is from Paul. It's, have you been able to identify a commercial lab in the Northeast that is able to analyze 6-ppd?
We have not done any work with that, so I don't know.
Okay, Makes it easy, but answered, Paul, asked and answered. So I'm going to move on to a question from Kevin. When planning new development, is there a clear
Yeah.
best distance that we should leave between buildings and wetlands to help protect our water? Great question.
That is a great question. I think I don't know about distance in terms of protection. Wetlands themselves are amazing protectors. So I think the key thing is just having wetlands there to help filter and clean water. A lot of kind of constructed wetlands can have the same kind of benefits as natural wetlands. So I think the key, and I know in Massachusetts there's a lot of, fill in this wetland, build a new one. Like keeping kind of native wetlands is really important. I don't know about distances between things though,
Thank you.
but keeping the wetlands is good.
Next question is from Andre. Did you look at the condition of sewer pipes and laterals in the upstream areas or at pharmaceutical residues like heart meds, for instance?
Yeah. So we have not. It's so hard to get data on even where all sewers are. And so we haven't been able to include those data in pretty much any of the studies that we've done because we're trying to do it over these large urban areas. And a lot of that information is kept at the municipality level. And so, for example, in the Boston study, Annika did a ton of work to try to just collect information on street sweeping, and it was 25 different municipalities that she had to like integrate. And it was just an incredible amount of work. So that's really hard to capture. We haven't been looking at pharmaceuticals. Um, there are lots of other studies that have, and there was actually a great study in the Baltimore area where folks looked at dissolved organic matter and they combined that with pharmaceutical measurements and used that to support basically dissolved organic matter signatures and the same kind of signatures that I was talking about today, like this protein like tryptophan fluorescence as indicators of sewage leaks.
I'm actually going to continue with Andre's questions because we did just speak about wetlands. Can you speculate further on why lost wetlands, particularly in the Boston area, are so important for water quality?
Yeah, so I mean, this study, we were looking at carbon, and wetlands are major sinks for carbon. So they are producing lots of carbon with those wetland plants, and then it's getting stored in those wetland soils, and basically hanging out there. And so any water that's going through a wetland, people have known for decades that wetlands, the kind of the prevalence of wetlands on the landscape is a huge predictor of how much organic carbon is going to be in your stream water.
Okay. Um, Carrie has a question. Are the SIGO data revealing a CSO or broken or inundated leaching fields?
So there aren't any combined sewers in that watershed. It was designed with a separated sanitary sewer and storm sewers. But there are a lot of, I didn't show this figure in the talk, and this is again the kind of challenge with doing large watershed studies where you have kind of different controls on data. Um, we haven't been able to look at sanitary sewer overflow data because they're collected differently for Maryland than they are for DC. And our watershed includes both. And it's basically going across state lines. But there are a lot of sanitary sewer overflows in that watershed. And I suspect that there are lots of leaks that are coming in just that we don't know about. There's also been a lot of construction on a new railway through that watershed. That's definitely impacted turbidity signatures. Um, And then there's all sorts of stuff that just happens, right? Like working with the riverkeeper is so great because they get calls all the time that are like, hey, there's a bus that's just emptying its bathroom like into the storm sewer, right? Like, so there's just kind of random stuff that happens as well, that can really impact the water quality, but are really hard to predict, right? Like you can't predict that some bus driver is going to decide to just do that.
Yikes.
Yeah.
Okay, and the last question, unless anybody else wants to weigh in, is from Jean, who would like to read the report that you mentioned a few times. Is there a link to it that we can use to get to it? And he's
So the
thanking.
one that Annika's paper, I can send that. I can send a copy of her paper, and then Allison has a paper also on conductivity, looking at the conductivity in those systems, and I can send both of those, and you can share them around.
Great, perfect, thank you. We have a question from Dan. Are you doing water studies to both reduce water use from HVAC and process, as well as ways for these water users to reduce hazardous chemicals?
We have not done anything like that.
Okay. Okay. And Gene is confirming that it's Annika's report that he's interested in, which we will be very happy to send around. Okay, unless there are any other questions, going once, going twice, I'm gonna send it back to Julia.
Oh, now I get to see your faces. I think it's actually Emily will officially close out our meeting because she's our board president, but this is my opportunity to say thank you for coming and thank you, Dr. Hale, for a great little presentation. Maybe we'll get you back in the future when you have more data to share. Um, yeah, thank you all. This is my last annual meeting, so it's been a pleasure to be part of the community. And I am now going to turn it over to our board president, Emily Sherbo, to officially adjourn us.
Thank you,
Okay.
Julia, for all your work.
Yes, that's what I was gonna say. Thank you, Julia. This is your last meeting, which I feel like I didn't think of that today, but round of applause. 16 plus years of awesome work at the helm. And yes, thank you to Dr. Hale. That was an excellent presentation. Um, so
And before I
oh,
go, of course, always interrupting people. Thank you to Monica for finding Dr. Hale and for leading us through the Q&A session too.
yes, thank you.
Great find.
Excellent. Okay, so to close out our meeting, I'm looking for a motion to adjourn. Would anyone like to make that motion?
I'll move to adjourn.
Thank you, Mary. Would anyone like to second that motion? Paul, I see Paul. Thank you. Okay, everyone in favor of adjourning the 2025 annual meeting, raise your hands. No one objects? Okay. Thank you. Meeting is adjourned. Thank you, everyone, for coming.
Thank you all.
Bye.
Thank you, everyone.